So I told you about our method. Now I want to show you one of the simulation studies from the manuscript. And the point of this simulation study is because this is a non-convex problem, we wanted to study how sensitive our estimates would be to different starting values provided to the optimization. So here we're in the linear regression setup. We have n equals 100 observations and d equals 5 explanatory variables or predictors. Beta is fixed at these values. And the test that we're doing is we're just incrementing beta 1 away from its MLE by a very small amount. And so because we're only incrementing away from the MLE by a small amount, we should expect that that test statistic is very close to 0. So here the data is fixed across all 100 simulations, but what we do is as I said before, we randomize the starting values. So we randomize the initial values for the weights, and also for the coefficients, we fix the first component to this value, and then the other components are set to their MLEs, but just we add some small uniform random noise to introduce the randomization. So these are the results from some of the results from this simulation study. So first I want you to focus on this panel A here. So these are the distributions of that log empirical likelihood ratio. As you recall, this was the quantity that we used to actually do the inference itself. Okay, and so first let's look at this nested algorithm here. So first I want to point out that this nested algorithm had actually diverged in 62 of the experiments. So I'm only showing you 38 of the experiments here. But even in these 30 experiments, look at the variation in these estimates, right? Now let's look at our proposed method, BICEP. There is some variation, but if you notice, it goes between like minus 0.4437 and minus 0.4439. And so what we can conclude is that our algorithm is much more stable than the nested algorithm in regards to these starting
values. It's on a
values.
different scale, okay? The y.
Yeah.
Y scales
Yeah.
they're different.
Take care to notice the scale. I mean, this goes from minus 600 to 0. Now here, what I've done is I've compared the primal residuals. So the primal residual, this is just the L2 norm of that structural constraint. If you recall, we wanted that structural constraint to be equal to 0, right? And so we want this primal residual to be small. And if we just look at BICEP here for a second, it seems like we're doing a pretty good job of satisfying that structural constraint. Of course, if you compare to the nested algorithm, the magnitude seems to be smaller, but remember that some of these points are corresponding to estimates that are just completely unreasonable. So I also wanted to show you all one of the real-world applications of our method. So here we're applying BICEP to the Human Microbiome Project. So this was a consortium through the NIH, and the basic idea was they just wanted to kind of get an idea of what are the various bacteria that live in different body sites of the human body. And so what they did was they took microbial measurements from various body sites of about 300 subjects. And they took these samples and they sequenced them, and then they clustered them into what are called operational taxonomic units, or OTUs. And so these OTUs, to you and I, we can just think of them as being different species of bacteria, okay? And so a very common research question in these types of analyses are, which OTUs are differentially abundant between body sites? So by differentially abundant, you can think of this as being, which OTUs are significantly differently found between body sites in a statistical sense, okay? And so here the body sites that we're going to focus on are the tongue and the throat. Here I just want to mention that we have 198 samples and about 45,000 OTUs, so quite a high dimensional problem, right? And so the way that people have traditionally dealt with this high dimensionality is, well, first, these OTUs, these are often thought of as count data. And so the way they deal with that high dimensionality is they actually just fit a GLM to test the differential abundance of each OTU separately. So this would be like I'm fitting 45,000 GLMs, and I just collect all of the p-values, okay? And so in these GLMs, it's a Poisson GLM because these OTUs are count data. And so we have the response variable as one particular OTU. And the explanatory variable would just be a dummy variable for the body site, and then we can include any covariates that we'd like to adjust for. So in our model, we included sex as a covariate, just control for the fact that it's often been thought that males and females fundamentally have different microbiomes. Like, notice here that this man seems to have like different like shapes in his body than the woman, right?
This is really exciting area of statistical applications. I really find it to be very exciting. You guys know a little bit, right? You have been to some talks.
I think we've had like 2 microbiome talks this
in
semester.
recent years.
Yeah.
Sure, you probably want to study an application here to apply some techniques we developed. But it's very exciting area, I can say. If you have interest, I would suggest everyone to study a little bit. You can actually do a lot of interesting discoveries at least.
Yeah, so microbiome, I would say it's really exploded maybe over the past 10 years or something like that. So in the 90s it was all DNA microarray.
But hold on. You know what this word is? Microbiome. What does it mean?
So microbiome, this is like a census. So this is like a census of the bacteria that live in some particular environment. So human microbiome, this is like the bacteria that live on the human body. But you could also have microbiome of the liver or something like that. So it's like you're just looking at the bacteria in some environment.
I want to say the Chinese, but
okay. Yeah, go ahead.
You can.
It's fine.
Yes.
Yeah. Okay, so now that we've had some translation, hopefully you guys have a better understanding of the problem that I'm talking about.
You can get a big amount of money if you study in this area.
Yeah, people have made some amazing discoveries in microbiome. Like for example, there's been studies that say that the bacteria in our gut actually has an effect on our mental health. So if you have the wrong type of gut composition, you might be depressed or something like that.
Oh, okay.
or maybe crazy, right? We don't know. But yeah, it's a very interesting area. And so these are confidence intervals constructed by 3 different methods. So first I should mention that each particular box, this is the confidence interval for that tongue-throat dummy variable for one particular OTU. And so here I'm only showing you the results for the top 10 most abundant OTUs just because we don't want to be looking at 45,000 confidence intervals, right? So here I'm comparing 3 different types of confidence intervals. The first is BS-CAL. This is the CAL confidence interval with the bootstrap calibration. CS is the CAL confidence interval with the chi-square calibration. And PROF, these are just the profiled parametric likelihood confidence intervals. So 2 non-parametric confidence intervals, both from our method, and then a parametric confidence interval. Okay. And so, kind of what I take away from this is it seems like the non-parametric confidence intervals tend to be larger than the parametric confidence intervals, right? So maybe in this real-world data set, perhaps some of those parametric assumptions, maybe they need to be relaxed a little bit, right? And so, interesting enough, even for some of these particular OTUs, your inferential interpretation, it might change depending on whether you look at the non-parametric versus parametric confidence intervals. For example, for this one, this parametric confidence interval, it does not encompass 0. So we might conclude that this particular OTU is differentially abundant between the tongue and the throat. But if you look at these other 2, it seems like they are actually touching this 0. So you would have a different conclusion, right?
We need an even better example here.
Yeah.
I hope so.
Yeah. I just wanted to sum up our contribution. So BICEP, it's a flexible and a modular algorithm for composite empirical likelihood. We have a very fast implementation, and most problems it executes in just milliseconds. We provided a general form for composite tests where through that omega 0 we can specify really any composite test that we'd like. But we also have additional simulations and applications in the manuscript, and we actually make an extension to outlier detection. So we introduce an additional parameter delta into that structural constraint, so that becomes a trilinear structural constraint. So we have the trilinear algorithm for composite empirical likelihood, or TRICEP, or the other muscle on Arnold's arm here. Okay. Now for future work, the examples I gave today were very strictly in that classical statistics regime where we have large n and relatively small p. But of course, in modern statistics, we often have p larger than n, so we'd like to make extensions to high-dimensional problems, like, for example, the lasso. We'd also like to show the distribution of the test statistic for more general composite tests. What I didn't tell you before was actually that that asymptotic chi-square distribution, it still holds, for example, like for the profile likelihood case, but not necessarily for like the inequality or interval testing case. And also in this this tricep, we were able to directly control the number of detected outliers through a tuning parameter called Q. But we would like to study how we can actually automatically tune that parameter. And so this is where I say, oh, you know, select the publications, blah, blah, blah. And then thank you.
Okay, the right balance, if you go to industry, even if you give a conference, give a presentation in an academic conference, you need the right balance. This is actually 1/3 or maybe 1/4 of what he presented his PhD work. This is definitely not his own. He didn't introduce the tricep, but even including the tricep is like only one of the 3 or 4 topics he worked with me during his PhD career. But you need to emphasize the most important one. You need to maybe give enough time to the basic things, motivation. Any comments or thoughts from you guys?
Before we get into that, I want to point out a couple things. So the first time I showed this picture, so I want to say that, you know, I actually took this idea from Eric Chi at NC State. So Eric Chi is a professor at NC State, and he was showing me some slides for his method. He has this method for biclustering called Cobra. And when he first introduced that method, he shows a picture of a cobra, like the snake, but then he has an extension called Cobra Pod, so it's a cobra with an iPod. And so, like, you know, that really stuck with me. So what I always try to do is, you know, you want to use these kinds of visual cues so that people can kind of remember certain things from your presentation, right? You know, it's not always going to work out where you have some name like this that directly corresponds to some funny picture like that. But, you know, you can use pictures to kind of keep the audience engaged, right?
Yeah, exactly. Yeah. You know, well, it's ironic because at first I didn't realize this is actually anyway. You need to make some good acronyms, some abbreviations. This is actually a nice thing. If you want your method to become famous, because well known, maybe you want a cool name as well. Well, remember years ago when we wrote the paper, we made the iPod thing. Actually, then people, oh, that's a cool name. Yeah, I never had it on again. Okay, any comments from you guys? Nothing? Okay, let's thank Hua for the wonderful presentation. Thank you so much. Thank you. Okay, this is the true end of this semester's club. I appreciate everybody actually coming to this presentation club every week, almost every week, right? Thank you.
Yeah. And my last ever GMSC presentation. You know.
Thank you. Okay, likewise.
咱们什么时候说5点交啊？咱们什么时候5点？
一般都是5点，不会
4点半写的呀，5点。
谁呀？
你他妈的，怎么？你还差多少呀？你还差个。